Today, we are going to learn about trends on the periodic table of the elements. Now, when I say trends, some of them include the noble gases, but some of them do not include the noble gases. So, for our purposes in honors chemistry, we're just going to exclude the noble gases. And let's talk a little bit about definitions first. Electronegativity is the ability to pull electrons in a bond toward yourself. So the most electronegative element on the periodic table of the elements, which you would have learned about in the periodic trends POGL, is going to be fluorine. That means he's the best at taking other people's electrons. So that's why when we first started learning about the trends, we put a star up here by fluorine, and we also put a star down here by francium. Now, I want to caveat francium. You're not going to see him on some lists of periodic trends. They might have listed cesium. The reason is that there's not a lot of data for francium. So we typically talk about things that we know. So when I say francium and fluorine, we really want to talk realistically about cesium down here. So fluorine is the most electronegative, meaning that when he forms a bond, he's the best at pulling on electrons that belong to somebody else. That's what electronegativity means. Ionization energy is the amount of energy to pull the tightly held valence electrons. So the valence electron that's held with the least amount of energy, that means I'm trying to pull it away from an element, and fluorine has the highest ionization energy also. Now, ionization energy is one of those ones that does include the noble gases. The noble gases all have very high ionization energies because they don't want to give up electrons. So ionization energy is a measure of how hard is it to take an electron away from an atom. First semester, we learned about atomic radius. And atomic radius is actually the distance from nucleus to nucleus in a bond. You take half that distance, and that's the atomic radius. So let's talk a little bit more about why. So I'm just going to randomly take the second principal energy level here, which is lithium through neon. And we're going to talk about what's going on here. So they're all in the second principal energy level. So they all have 2 electron shells. So that's not what's governing the trends here because they all have 2 electron shells. And I'm just going to draw them fairly poorly so you guys can see what's going on. So they have the same number of electron shells. They're in the same principal energy level. So that's not different about any of them. What is different is that we're adding protons to the nucleus. So what's governing the trends in the periods going from left to right across the periodic table is going to be called the Coulombic effect. So anytime you're describing why the trends are happening from left to right across a period, it's going to be called a Coulombic effect. And the Coulombic effect is caused by the increased nuclear charge as you go from left to right. The increased nuclear charge means that I have more protons in the nucleus or more plus charges in the nucleus. Those plus charges in the nucleus are what we're talking about when we're saying that an atom is hanging on to electrons. Opposites attract, so the positive protons pull on the negative electrons. And that's what chemistry is all about, is the movement of electrons. So that's the reason why, as you go across the period from left to right, the atomic radius is going to decrease. So in a period, the largest atom in a period will be the one that is furthest to the left. In the case of the second principal energy level, it is lithium. So connect in your brain the Coulombic effect with increased nuclear charge. or protons are being added to the nucleus. So these protons added to the nucleus make it so he hangs onto his own electrons with more energy, therefore he pulls them closer. It makes it so he hangs onto his electron with more energy, so the ionization energy will be higher. That's the measure of how much energy you have to spend to take that last electron away from an atom. It also means the electronegativity increases as you go from left to right, because the protons in the nucleus are able to pull on other people's electrons more because of the small size. So this element up here, fluorine, is going to be small. It's going to be highly electronegative. It's going to have a high ionization energy. And then there's two other trends where it talks about metallic character and non-metallic character. If you remember, metallic character means that it is shiny, ductile, malleable, and it's a good conductor of heat and electricity. Non-metals are dull, brittle, and they're insulators. So that's what we mean by metallic character and non-metallic character. So fluorine has the highest non-metallic character and the lowest metallic character. Now let's talk about what's happening as we go down a family here. So I'm going to start with hydrogen here, and then I'm going to go to lithium. Now, here's what's happening here is as we're going down a family, electron shells are being added. So these electron shells that are being added are going to shield the valence electrons from the pull of the protons in the nucleus. So what that means is as you go down a family, the size increases, so the atomic radius increases. The electronegativity decreases, and the reason for that is because the valence electrons on the outside are shielded from the pull of the protons in the nucleus by these full electron shells. So here's the valence electron. Each of the alkali metals and hydrogen all have one valence electron. That valence electron is held onto by the protons in the nucleus, the positive protons in the nucleus. But in this case, there's a lot of electron shells that are shielding this electron from the pull of the protons in the nucleus. Because of this, the atomic radius increases, the ionization energy decreases, and the electronegativity decreases. That means that the further down you go, the easier it is to pull a valence electron away. The further down you go, the less energy you have to spend to pull an electron away. The further down you go, the less ability these atoms have to pull on other people's electrons. And they also can't hold their electrons very close because of those full electron shells. So that means that our ionization energy is low, our electronegativity is low, and our atomic radius is big. So we'll call this, all these trends that occur from top to bottom in a family, all of the families except for the noble gases, are going to be caused by the shielding effect. So you should be writing down, you should have written down the Coulombic effect, and you should also be writing down the shielding effect and what it means. That'll be something that you need to know. So let's pick cesium down here, and we're going to say that cesium is large. It has a low ionization energy, has a low electronegativity, and it has high metallic character and low non-metallic character. So high metallic character for fluorine means that it is highly electronegative, high ionization energy. It is small, it is dull, brittle, and it's an insulator. Down here, cesium, the other, is large, has a low ionization energy, a low electronegativity. It has high metallic character, and it has low nonmetallic character. And those are a summary of our trends. You got to know the difference between the shielding effect and the Coulombic effect. So here's a list of the atomic radiuses, a picture of the atomic radiuses so you can see this. Now, the noble gases do tend to follow the atomic radius trend. The trend that they do not follow is electronegativity. So you got to remember noble gases have a full electron shell, a full valence shell. So they don't want to take anybody else's they want to take anybody else's electrons. That's why they don't have electronegativity values. They don't want to give up any electrons, so they have high ionization energies. And their sizes tend to be where you'd expect them to be. So if you notice down here, what's noticeably absent is these couple elements right here. And that's because there's no real values for them. If you look at them on the periodic table, the elements, you'll see their molar masses are in parentheses. And that means that we can't get accurate data on it. So we can get estimated data. And that's what the parentheses mean around an atomic mass. So here's just a picture of the atomic radiuses. And if you see the atomic radiuses in actual numbers, they will follow these trends. Now, I do want to point out when we say the word trends, that means that they generally follow these rules. So what that means is like, we're in February here. It's usually pretty cold, right? But that doesn't mean it's going to be cold every day. Like supposedly it's going to be 60 towards the end of the week. So even though it's not usually 60, sometimes there's a variation from the trend. It is usually cold in February, but there are occasional distractions from that. And that's the same thing that's going to happen with the trends on the periodic table of the elements. There'll be a few exceptions here or there for other reasons that we're not going to worry about at this level. So that's a summary of the trends that you're going to need to know that are going to lead us into using these trends for bonding.